Hey guys, so in this video we will have a look at another very standard dynamic programming problem, that is the rod cutting problem. So the problem is, given a rod of length n and an array p of size n consisting of prices of the rods of size 1 to n, find the maximum price you can sell the rod at. Given you can cut the rods into rods of smaller length. Alright, so for example, let's say initially you were given a rod of length 5, you are allowed to cut it down into rods of length, let's say 3 and 2, such that their total sum is still equals to 5. And another way to cut a rod down of length 5 will be into rods of length 2, 1 and 1. So now I hope that the problem statement is crystal clear. So I will try to explain this test case over here with the help of an example. So for this test case over here, n is equals to 4, that is length of the rod is equals to 4, and the prices of the rods of length 1, 2, 3 and 4 are 1, 3, 4 and 5 respectively. Alright, so these are all the ways to cut down the rod into rods of smaller length. Alright, so for 4 rods of length 1 each, the total price will be equals to 4. For 2 rods of length 1 and 1 rod of length 2, the total price will be equals to 2 plus 3, that is equals to 5 over here. Now for 1 rod of size 1 and for 1 rod of size 3, price will be equals to 1 plus 4, that is equals to 5 again. For 2 rods of length 2 each, the price will be equals to 2 into 3, that is equals to 6. And for a single rod of length 4, the price will be equals to 5. Alright, so among all these cases, the maximum price is of the set 2, 2, that is answer is equals to 6 in this case. Alright, so I hope that this test case over here was clear. So let's try to understand the code now. So we will use this main function over here to actually take in the inputs and pass in the inputs as a parameter to max profit function to get the final answer. Alright, so let's say the first line of input contains an integer n and the second line of the input contains the price array. Alright, that is up to pn. Alright, so let's just take in them as an input. First line of the input is an integer n, so let's just take in that, and the second line of the input is an array of size n. So for that I would iterate over all the indices from int 0 to n minus 1, and I would take them as an input into p of I. Alright, and then all I need to do is I need to call this function max profit with the parameters n and this array p over here. Alright, so now all we need to do is we need to complete this function max profit over here. Now in this video we will try to solve this problem using tabulation. Alright, and in the previous videos we have already discussed that whenever we are trying to solve a problem using tabulation, we divide the problem into 3 different subproblems and then we integrate them into a code. Alright, so the first subproblem was defining the states of the DP. So in this case we are going to define DP of I as the maximum price for a rod of size I. Alright, so let's say max price for a rod of size I. Alright, so from this definition it's evident that our answer is nothing but DP of n, that is maximum price for a rod of size n. Now coming to the recurrence relation part, so DP of I will be calculated as max of P of j plus DP of I minus j for all j between 1 to I. Alright, so this is the recurrence relation over here. Let's try to understand this recurrence relation over here with the help of an example. Alright, so let's say we have a rod of length I. Alright, so from this rod of length I can chop out any other rod of length j. Alright, so let's say I chopped out a rod of length j and sold it. So the price for the rod of length j will be equals to P of j, and then I would have to solve this problem for the remaining rod of length I minus j. So for that the price will be DP of I minus j from the definition. Alright, so I have to maximize this value for all the j's between 1 to between 1 to I. Alright, so that's why answer becomes DP of I becomes max of P of j plus DP of I minus j for all j's between 1 to I. So I try to briefly explain this recurrence relation over here. Now the third subproblem was laying down the correct topological order. Alright, so for understanding the topological order, or we should look is at the recurrence relation. Alright, so if we have a look at this recurrence relation over here, we would realize that dp of I, it actually depends upon all the indices j that are less than I. Alright, so that is derivable from this recurrence relation over here. So the order in which we should solve the states is 0, 1, 2, 3, 4, 5, 6 and up to n. Alright, so we will all solve the states in the order of dp of 0, dp of 1, dp of 2, dp of 3, dp of 4 and up to of dp of n. Alright, and dp of 0 in this case will be our base case. Alright, and its value will be equals to 0 because the price for a rod of length 0 will be equals to 0. Alright, now that we have solved the three sub problems, let's just integrate them into a code. So the first thing that we would need is an array dp of size n plus 1 to actually represent the states of the dp, and then we would initialize the base case as dp of 0 equals to 0 as we had discussed in here. Now we would solve the states in the increasing order of the states. Alright, so for that we would iterate over all the states from I to n, and we would, in each iteration we would try to solve the ith state over here. So initially let's just initialize the value of dp of I equals to 0, and then we would iterate over all the indices j between 1 to I, and for each such index j we will try to update the value of dp of I as dp of I equals to max of dp of I comma p of j minus 1. So this p of j minus 1 actually represents the price of the rod of length j. Alright, so actually since this is a zero based indexing over here, this price array, this array over here follows a zero based indexing. So the price of the rod of length j is represented by p of j minus 1 in here. So that's why we are using p of j minus 1. Otherwise, if this were one based indexing, we would have used p of j over here. Alright, so this will be equals to p of j minus 1 plus dp of I minus j. So this would actually represent our recurrence relation, and this and thus we are actually solving, this is how we actually solve the states of the dp in this case. So in the end, all we need to do is we need to return the value of dp of n from the definition of the states. Alright, so this is the complete code for this problem over here, and let's see if this works or not. So now if we actually try to compile this code over here, so let's just try to compile this code over here. So for these test cases over here, that is 4, 1, 2, 3, 4, our answer is equals to 4, and that is correct. And for the second test case, that is equivalent to the test case we represent in the sample test cases, the test case is 4, 1, 3, 4, 5, and for this the answer is equals to 6 as we discussed. So this is how we code up this problem over here. Now coming to the time complexity analysis of this code, we have n states in total, and each state takes O of n time on an average to solve. So the time complexity becomes O of n square. Alright, and the space complexity in this case will be equals to O of n. Why? Because if you notice, we are only using a linear dp array to actually solve this problem. So the size of the dp array that we are using is equals to n plus 1. So that's why the space complexity is O of n over here. Alright, so that's all for this video, guys. Hope to see you guys in the next videos.